Hello and welcome. Today we're going to look into DNF simplification, Karnaugh Maps, also known as K-Maps. But before, I really recommend that you watch my video called DNF and CNF before watching this one. It will definitely help you. I'm going to start with an example. Here I have an expression, Boolean expression, and I need to write it in DNF form, sum of product. The first step to do is to create this truth table. Once you do it, you look at your truths here, 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 and see where they are coming from. This first one here is coming from T, and that produces P and Q and R. This one here is coming from T, F, T, and that produces P, not Q and R. And you finish those. The last one, this one here is coming from F, F, T, not P, not Q and R. And then you put between them the OR, and you get this expression. So that's sum of product. So I wrote this expression in form, in sum of products. Now, the question is here, why would anyone with a sound mind take a simple expression like this and blow it up to be like this? It makes no sense. So why would anybody take this really simple one and turn it into this complicated one? The reason being is, we'll see that in a few minutes here. So I'm going to take now another example. A committee of 3 members decides issues by simple majority vote. A proposal passes if it receives at least 2 yes votes. So here you see I do not have the function. I have input and I have output. But I can always create a function, a Boolean function that satisfies these values. So all what I have to do is write it in terms of sum of products. So again, look at the T here, T. That's a proposal. When you have yes, it passes. Yes, no, it passes. Yes, no, yes, it passes. Yes, no, it doesn't pass, and so on and so forth. And then you write this into sum of product. Again, see that one here is sum of product. So now I found a function that satisfies these values. So that's why in practice we do not have really the function. In practice, if I go back here, in practice I do not have this. I don't have this. I don't have it. I have values like that, T, F, T, input, output. I can always create a function, but then I have to find a way to simplify it if I can. And that would be very helpful, especially if you are building circuits. You need the least amount of operations to use. And we will learn how to simplify something like this. Okay, so now the ideas, the rules behind the simplifications are very simple. The first one is P and not P is always true. P or P is the same as P. How do we use this? This tells me now if I repeat a term in an expression, it will not change its value. And we will see how that's going to be used. P and T is always P. And this one here is the distributive law, P and Q, P and R, and you put or in the middle, P and Q, P and R, and you put Q in the middle. That's the distributive law, and we will use that shortly. So here's an example. I need to reduce, simplify, if possible, this expression. I notice that P is here and here, so I can take it out. That's the distributive property. Then inside, I'm left with Q or not Q. Now, Q or not Q is T, true. Now, P and T is P. So you see now this one here is simplified to be P. Another example here. Here I have three terms. So I'm looking at two terms that differ in only one of the variable. So if you look at this here and look at this here, only Q changes. So I'm going to use this term and this term to get some simplification. And also, if you look at this term here and this term here, the change is in only one variable, in P only. So what I'm going to be doing here, I'm going to use this here twice. This one here, I'm going to use it with this. And look, Q cancels Q. Q cancels Q, and I'm left with only P. Now, this same term, now, I'm taking it with these two here now, which means I am repeating this term twice. See, I could have put it back here if I want to, or P and Q, and it won't change the value of the expression. Then I can use these two together to simplify. So now when you take the first one and the last one now again, so let's clean this up here. You get what? You get P cancels with not P, you get Q. So the answer will be P. The answer will be P or Q. Okay, so that's a clean version of the answer here. Now, here's an example where you have 1, 2, 3, 4. You have 1, 2, 3, 4, 5 terms. These two terms here, they differ in only P, see, in only P. Then they are reduced to Q and R, Q and R. This one is used again a second time with this because they only differ in R, see, R, not R, and that will produce not P and Q. If you look at these two last ones, they change, the differ is only R and not R, so the answer will be not P and not P and not Q. Now I notice that these two, they differ in only Q. So that will be reduced to not P. So the answer will be not P or Q and R. Very simple. Not P or Q and R. Here's another example. This is the one, the voting result that we just did before. So we wrote it into sum of product. Now I'm going to simplify that. So I noticed that this first term here, P and Q and R, with this term, the change in only R, see, in only R. So therefore, I get P and Q. Okay, I get P and Q here. Now, if I take the same term, the first term, again with this now, look at them, the difference is in Q. Q, not Q. Then the result will be P and R. Now I'm going to take the same one, the same first term here with the last one. And the change is in P only. That will give me Q and R, Q and R. And therefore my expression is reduced to this simple one. So now this method is obviously not very practical, but it does work, especially if you have a large number of variables. It does work, but we're going to introduce a method that is more easier to use for small values of small sizes of variables. So this is called the Karnaugh Maps. So the idea here to use the largest blocks of adjacent. adjacent, very important. 1, 2, 4, 8, 16, etc. So multiples of 2, except for 1. And then terms to reduce, or terms to reduce each block to one term. And this graphic method can be used up to 6 variables. But in this video, I'm covering 2, 3, and 4 variables only. Okay. So let's start with this. Now we're starting with 2 variables. Okay, the 2 variables, you make a table like this, okay? Now here you have P, not P, Q, not Q. And now we're going to map our expression. You have P and Q. P and Q, you put the number 1 or a star or a dot, just mark this box here. And the other one is P and not Q, P and not Q. Now the idea here is to cover all these dots by the largest possible blocks of 2, 4, 8, etc. So here you have to take these 2 together. If you take these 2 together, Q cancels not Q, the answer will be P. Okay, look at it here in red. So we create the K-map. We map the expression. I got these 2 stars here. I block them, the 2 together. The answer will be P. Here's another example. Let's map this. P and Q is right here. Not P and Q is right here. Now you need to take these 2 together. Okay, so let's look at it here. In blue, that's the K-map. And in blue, what happened now? These two canceled each other's. The answer is Q. The answer is Q. Another example. Let's have 3 terms here. P and Q, like there. P and not Q, here. Not P and Q. So now I have 3 of them. So you need to cover them. Obviously, to reduce this term, you have to take it with this. So you have to take these 2. Now, to reduce this term here, to reduce this one here, you have to take it with this. So it's more like this term was used twice, 1 here and 1 here. And see here is a nicer color here, a nicer picture of it. So the green will produce Q because P not P cancel, and the blue will produce P. So the answer will be P or Q. Here is another example. I have 4 terms now. P and Q, right here. P and not Q. Not P and Q. Not P and not Q. Okay. So obviously, I mean, you can take these 2 and these 2. It's a simplification, but it's not the final simplification. What you need to do is you need to have the largest possible blocks, 2, 4, etc. So you can take the 4 of them together here, and the answer will be true because P cancels not P, Q cancels not Q. Okay? This expression is a tautology, it's always true. This is an example where there is no possible simplification. Those are not adjacent. They have to be adjacent. This one and this one are not adjacent, so you can't do anything about it. The expression stays the same. Now let's look at 3 variables, a little bit more interesting. Here's an example. Now you create this table. Now you need to be careful here. Here, P, not P. Look at this, Q and R, Q and not R, change in only one variable. Look at this one here, Q and not R, not Q and not R, change in only one variable. Look at this one here and this one here, change in only one variable, only R change, see? Now, if you look at this one and this one, also change in only one variable, which is Q, not Q. Now, if you put this term here and this term here, it won't work. It has to be in this order. Any adjacent terms, they differ in only one of the variables. That's very, very important. So now let's fill up our table here. You have P and Q and R is right here. P and Q and not R right here. Not P, not Q, not R. Not P, not Q, R. So obviously now you have to take these two together and you have to take these two together. Okay? So the green, when you take these two together, what happened is from here you have not P. And from the top, R cancels not R, you are left with not Q. So the green will give you not P and not Q. Look at the blue now. Blue. Here you have only P, see? P. And on top, R cancels not R, Q, P and Q. And that's the answer. Here's another example. Let's map it. P and Q and R. P and Q and R right here. P and Q and not R. P and Q and not R. Not P and Q and R. Not P and Q and R. Not P and Q and R right here. Not P and Q and not R. Not P and Q and not R here. It's good practice as you are mapping those terms is to mark them that you did. This way you don't forget one of them, or you don't double one of them or forget one of them. Here, not P, not Q, not R. Not P, not Q, not R right there. Here, not P, not Q, R. Not P, not Q, R right here. Now, group of 2, 4, the largest possible group. So you have to take these 4 together. Now, you can take these 2 together, but that's not really the best simplification, because you can take these 4. Let's look what happened now. The green, look at the green. You have not P here, and all of this cancel each other. So you're left with not P. Okay. Look at the blue now. Look at the blue. Here, P cancels not P. Look at the top here. R cancels not R. You are left with only Q. So that's the answer. Okay, now a situation like that can happen. You have 2 here and 2 here. Now remember, those are also adjacent, because look at Q, not Q, only one variable changes. All right, so to understand this, I made this graph for you, and look at P and Q is here. P and Q is here. P and not Q, not R is here. Q and not R is here. Not Q and not R is here. And not Q and R is here. See, they turn around. So these two are neighbors also, are adjacent. So now, when you do that, let's screen this here so we can see better here. So when you do that, what happens is you're going to be here, P cancels not P. On top, you have Q cancels not Q, and you're left with only R. Let's do this here now. P and Q and R. P and Q and not R. P not Q R. P not Q R. Not P Q R. Not P Q R right here. Now when you look at it, this term here, the only way to reduce it, you have to take it with this. You don't have any other option. So you have to take these two. Now this term here, in order to reduce it, you have to take it with this. Okay, you have to take it with this. Now don't leave this one alone, because this one is neighbor to this. So you end up having 3 terms. And here's the situation here, and you can easily find this to be P and Q, or P and R, or Q and R. And that's the same as the example for the vote result. So we created that, and we simplified it to be this. Another example, P and Q and R, P and Q not R, P not Q not R, P not Q R, not P Q R, not P and Q and R right here, not P not Q and R. All right, so this is really, again, very straightforward. You have to take these 4 together, and you have to take these 4 together. So when you take the green, from the left-hand side, you get P. All the top part cancel, so you get a P. Now look at the blue now. The blue here, P cancel, not P. On top, what happened? Q cancels, not Q. You're left with R. P or R. Here, P and Q and R. P not Q, not R. P not Q, R. Not P, Q, not R. Not P, Q, not R. Not P, not Q and R. Not P, not Q and R is right here. Now here you notice that this one here has to stay alone. It doesn't have any neighbors. So this one is boxed by itself. Now to reduce this, you have to take it with this. To reduce this, you have to take it with this. Now to reduce this, you have to take it with this. Group it. Okay, use green here. So you notice that this term was used 3 times to reduce this, to reduce this, to reduce that, as if it was repeated 3 times. And easily now you see the result. You see how this term here stays the same. Okay. Okay, now if it happens that you fill all these 8 squares, rectangles, the answer will be true all the time, and that's a tautology. Okay. Now, it's if you take only, let's see here, let's do this. If you take these 4 and these 4, you get an answer, but that's not really the simplest form possible. Okay. You have to take the largest grouping. Now, sometimes you have a situation like this, no possible reduction. There's no neighbors at all here. Now, the question sometimes asked is there sometimes more than one simplification to the same problem? Yes. If you look at this here can be taken with this, or can be taken with this. And therefore, you get 2 answers. So this first are the same, but changes is in here. But these 2 are equivalent. Now we're going to move to more interesting situations for variables. Okay, so now again, I want to make sure you understand how those are arranged, because if you make a mistake in arranging those or those, it doesn't work. It won't work. look, from here to here, change in only one variable, s minus s. From here to here, change in only one variable, r minus r. From here to here, change in only one variable, minus s, not s, s. From the first one into the last one, check it again, change in only r. See, change in only r. The same thing here. Between these two, change in q. Between these two, change in p. Between these two, change in q. Between this first one and the last one, change in p. This is very, very important. So now if you have this 8 situation here, or what you have to do, block all of them 8, what happened? All this left side, all this cancel. On top, you have r cancels not r, and the answer is not s. This example here, you have 2 blocks of 8. The green, you see here, the green is all of this cancels, and then on top, s cancels not s, you get an r. The blue now, the same thing, all this cancels. On top, you will get the blue, r cancels not r, you get not s. Here's a situation where you have 4 here and 4 here. Again, very simple. For the green, for instance, on the left-hand side, q cancels not q, you get not p. And the top, watch the top here, go to the top here. Go to top, s cancels not s, you get an r. The same thing you do for this one, and you get this answer here. Now, if you have situations like this, you have to take this 8 together, the green. If you take this 8 together, the green, so what happened is, you look at the left-hand side, q cancels not q, you have a p. On top, all of them are canceled. Now, if you take the blue, all of these are canceled. All of these are canceled. On top, what happened? R cancels not R, you get not S. Now, if you have a situation like that, obviously you have the green here, all these 4, and you have this stays by itself, no neighbors. This one here, the only way to reduce it is to take it with this. And you have to take, remember, these 2 with these 2. And now easily you can find out the answer is right here. If you have a situation like that, obviously you have to take 8 of them. This here and this here. Then what happened? All of this cancel. On top, R cancels not R, you get an S. I will finish with this example. So we have an X is a 4-bit input integer represented by the 4 Boolean variables X0, X1, X2, X3, and Y is X plus 1. I want to find the values of Y1, Y0, Y1, Y2, Y3 as Boolean expressions of the Boolean variables X0, X1, X2, and X3. And for this example, we're going to represent 15 plus 1 by 0, 0, 0, 0. So first of all, let's look at this this table here. And your X is going from 0 to 15. And this is the Boolean representation. So when X is 1, it's represented by 0, 0, 0, 1. Then Y will be what? 2. This is a representation for Y. If X is 5, is 0, 1, 0, 1. Y is 6, 0, 1, 1, 0. And so on. 11, 1, 0, 1, 1. 12, 1, 1, 0, 0. And this question here is, example is we need to express those Y0, Y1, Y2, Y3 as functions of X0, X1, X2, and X3. So first of all, what I'm going to be doing here is I'm going to create this table here. This is really important because what happened is I put the same format as the one before, the K map before, for 4 variables, but I filled up here the table. So now, for instance, if you take 3 is 0, 0, 1, 1. If you take, say, 8 is 1, 0, 0, 0. If you take the 1 here, is 0, 0, 0, 1. So I create this table, which is going to help me quite a bit. Okay, so let's clean it because we're going to come back to it. Okay. Now, how to find Y0? If you go back to the table there and look at your Y0, see 1 here, 1 here, 1 here, 1 here, etc. See, when you look at the corresponding here, X 0, 2, 4, 6, 8, etc. So when you go there and put that here, so to calculate Y0, you have 0, 2, that's where they are, okay? So you group them all together. You group them all together. So what happens, all of this cancel. On top, X1 canceled not X1, and you're left with not X0. See, that's your answer right there. But for Y0, it's really easy to see that without having to go to do this map, because if you look at Y0 here is 1, here's 0, the opposite of it. 1, 0, 0, 1, 0, 1, 1, 0. So that's really easy to see, okay? It's not as easy now to find the expressions for Y1, Y2, and Y3, okay? So I need to clean this up because I need to go back to this here. Okay, now, so we did Y0, let's do Y1. Y1, to do Y1, you go back to the table and you find Y1. Let's do it here because we don't have to do it for Y2, because Y1, look at the ones here. Here, 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 here. 13, 14, 9, 10, 5, 6, 1, 2. And you go back there to the table, to this table, and pick up those what you want here, and you put them here. So now, obviously, you have to do 2 groups, in this group and this group. In both situations, all of this cancels. On top, you're left with X1 here, and not X0. The other one is not X1 and X0. So we did Y1 is done as a function of X0, X1, and X0 and X1 here. Now, we are going to do Y2. Y2, if you go back to the table and you find it's corresponding to 3, 4, 5, 6, 11, 14, 12, 13. So once you put this map it here, it's now easy to see that 3 and 13, 3 and 11 together, and that will produce this term here, because X3 minus X3 is gone, black. Look at the yellow here. The yellow here, those are neighbors. Those are neighbors. So up and down are neighbors. So what happened here, X3 is gone. You have X2 and not X0. On top here, X1 is gone. So you get that here. The blue, up and down, X3 is again gone. You have X2, and on top here, X0 is gone, and not X0, not X1. Now, it so happened that here X2 is common, so you can get it out to use, and using distributive law, and well, now we have Y2 as a function of X0, X1, X2, X3. There's no X3 here, but that's fine. The last one now is the Y3. So if you go to, again, just to remind you, if you go to Y3, look at Y3 now. Y3 is 1 is in this situation here. So what's 7, 8, 9, 10, 11, 12, 13, 14. So I'm writing them as a sum of products. Remember, that's what I'm doing. I'm looking at the one here. Okay, so Y2, Y3. All right, you put them around here and just find the largest possible grouping. The blue is X3 and not X2. X3 and not X2. The yellow from the left, X2 cancelled, not X2, you have X3. On top, this X0 and not X0, I cancelled, not X1. And the green is the same thing. And then what happened is, you notice now that X3 is here, here, and here. You can get it out and use the distributive rule to get this answer. So we wrote each one of them as a sum of product, and then we mapped it into this K-map, and we reduced it. That's what we did. Okay, because like 13 is X3 and X2 and not X1 and X0. That's what this means. Okay, 7 is not X3 and X2 and X1 and X0. And that is the end of the DNF simplification. Thank you, and we'll see you soon.